Hello, everybody. Welcome to today's lecture. As some of you might have known, this is our STEM lecture series. So welcome to Naxxatra. Today, we are really excited to have Swagat Saurav with us. Cosmology is one of my personal favorite subjects, and I think a lot of you might find it fascinating as well. So it's really great to have a cosmology talk as part of our lecture series. Swagat is from IUCAA. He's a senior researcher over there. His main field of research is in early universe physics and cosmology, and his recent work has also involved primordial black holes. So I think we will learn a lot in today's session. The format of it is similar. We will have a 30 to 40-minute introductory talk by Swagat first. And immediately after that, we'll have a Q&A session. So those of you who are watching us live on YouTube, you can submit your questions there, and we will try to address most of them. So let's get started. And before that, just to let you all know about what we do here in Naxxatra Sciences. It's a collaborative research platform, and recently we've started introducing a lot of useful courses, mainly for senior undergraduates and those who want to learn research skills. So everything from Python for scientists and engineers, all the way to advanced astrophysics, specifically in observational astrophysics, data-driven astronomy, and so on. And the big announcement coming up is that we have launched our Equinox program, which is starting on the 12th of September. So this is basically a 30-day astronomy school. It's an advanced astrophysics school for anyone who's interested to learn a lot in a more condensed form. There will be more than 20 to 25 lectures throughout the program. We will be covering a wide array of topics. And along with that, you will be constantly in touch with the mentors. And we have also planned on 4 different mini project tracks, including pulsar detection, orbital mechanics, and so on. So you can pick what mini project you would like to do, and you will be connected to a group of people to collaborate with, like-minded peers. So I think it's going to be a wonderful experience for everyone, including the instructors as well as all the students involved. So if you're interested to join Equinox, we will just leave a description, link in the description on YouTube. You can also get in touch with us through Telegram. So we will leave that link as well. So without much further ado, let's hear from Swagat. Welcome to Naxxatra.
Thank you very much. I hope I'm audible to everyone. Welcome to this summer monsoon evening lecture on a Sunday. And I'm going to talk to you about something very interesting, which is exploring inflationary cosmology. So I'm going to talk to you about cosmology, and particularly about inflationary cosmology. Okay, so let's get started. So I'm going to talk about roughly for about 40 minutes, and then we'll take some question answer session. I'll try to explain you some of the interesting concepts of inflationary cosmology. This is a little hard subject, conceptually a little hard, but we'll try to understand it in a semi-technical way. Now, I'd like to start by first wrapping up what we know about our universe, which probably is a common knowledge by now, but it's important to get into the scene by first understanding what we already know. So our view of the universe has changed from thinking that Earth is the center of creation and everything revolves around Earth. From there, by the Copernican and Galilean revolution, to the heliocentric view that Sun is at the center and everything else is rotating. In fact, as late as in 1800s, when William Herschel made a map of Milky Way galaxy, he put our Sun as the center of our galaxy and hence the center of the universe. So even as late as that, we didn't know. But later we figure out, okay, there's a galaxy around us and we live in that galaxy, and our position with respect to the galaxy sort of off center. So we're sort of like towards the edge of the galaxy. So we are around 8 kiloparsec away from the galaxy. So it takes a lot of time for light to reach us from the center. So we're not at the center of our galaxy. From there, we went to discovering that there are so many galaxies in the universe. In fact, we know there are at least 10 to the power 11, 100 billion galaxies in the universe. And if I look at the sky, and I have a good telescope, let's say Hubble Space Telescope, and I project it about one about the size of the moon, so it's 1 square degree, I would see about 10,000 galaxies like this. This is a real image. So you see in a small patch of the sky, there are so many galaxies. So you could easily say that the universe is filled with galaxies. This is what we see, the universe today. It has changed from there to here. And so we call it island of galaxies. And this is a small patch, but suppose you had a very wide vision. You could see a bird eye view of the universe. What you are going to see is actually this kind of spider net structure in 3 dimensions. Okay, and you see some filaments, then you see some very, very bright points, and then you see some dark voids. Okay, each point here, each dot here, each white dot here in this diagram, you can think of it as a galaxy. Okay, so if you look at the universe on a large angle, on a bird eye view, this is how the universe looks. In fact, we call it the cosmic web. It's a technical term in cosmology. And I should tell you that this is not a real image of our universe. It's not a photograph. It's actually a computer simulation. But if you could take a real image of our universe, it would look very much like this. Okay, this is what is the large-scale structure of our universe. This is how our universe looks today. But then the question comes: okay, this is how it looks today. But is our universe static and eternal? Like, has it always been appearing like this? Or is it evolving like a human being, which born as a baby and then evolves into a adult? We don't. Do we know? The question is very much yes. That our universe has been actually expanding. It's not static like this. It's been expanding, and just this one fact would lead us to a lot of findings in cosmology. So we start from this basic fact that today we can see lots of galaxies in the universe, and they are all expanding. Okay. I'll define what exactly is the meaning of this Big Bang theory, because I have met physicists also who had confusion over the definition of Big Bang theory. So I hope that by the time the talk ends, you would know for sure what do we mean when we say Big Bang theory. Okay. And most probably your earlier knowledge, most probably, would be a little erroneous. Let's see. So let's first think about Einstein's theory of gravity. We had the good old Newton's theory of gravity, which I presume that everyone here knows, that gravity is an attractive force, necessarily attractive force, and it is created by masses. So you have to have a mass to have gravity, and it will always be attractive. Okay. But in Einstein's theory, things changed. First thing is, gravity is not just due to mass. It could be due to any kind of energy and pressure and momentum and viscosity. Okay. So if I have any kind of energy, even if mass is 0, I'll still have gravity. So a photon, which doesn't have gravity in Newton's theory, will have gravity in Einstein's theory. The second thing is that gravity is not really a force, but it has to do with the curvature of space-time. So what happens is, given what kind of matter you put in the universe, what kind of energy, what kind of pressure you put in the universe, depending on that, the distance between 2 points in the space-time is going to change. It's going to take a different kind of formula. Okay, so there is no force really. You're putting matter and bending the space, and in that bent space, you are traveling in the shortest possible way. But that shortest possible way in the bent space looks to your classical logic as a bent line in a normal flat space. Okay, that's why you think that okay, planets are rotating around sun because they are bending. But in Einstein's way, there is no force. Sun is not pulling Earth. Sun is just bending the space. And in the bent space, an ellipse is really a shortest path. Okay. So it has to do with distance between 2 space-time points. And distance between 2 space-time points is no more given by your good old Pythagoras theorem. The second thing, which is interesting about Einstein's theory, is that gravity can be both attractive and repulsive. So it's not just always attracts, it can be repulsive also, which we'll see. And in fact, this is a theme of our talk, that gravity can be repulsive. And it can be, gravity can be sourced by massless objects, because all you need is energy, mass is not necessary. So photons can create gravity. Fantastic. Examples of Einstein's theory of gravity, one of the examples is a black hole. So what you do is take a lot of matter and compress them. Take a star, for example, and compress them and make a spherical object. Okay, very dense. If you compress them, the space-time around it will be bent in a very funny way, and all sorts of funny effects happens. Today's topic is not based on black holes. Maybe some other time I'll discuss this. But let's go on to another kind of situation in Einstein's theory. That situation is when you take matter, whatever matter you have, let's say atoms and molecules. Okay, you take them, maybe light, photons. You take them and you distribute them all over the universe in a sort of more or less homogeneous way, like in a uniform way. Okay, you distribute them everywhere. Then Einstein's theory says in this situation, the distance between 2 points in space will be almost like your Pythagoras theorem. So it's almost similar, but not quite. It will be time dependent. So your formula is going to be time dependent. So if I take just 2 points in space, the distance between them is not given by Pythagoras formula. It will be that formula multiplied by a time dependent quantity. So the distance is going to be time dependent. Either it will increase or it will decrease, or it is going to oscillate and increase for a while and decrease for a while. We'll see what it is. Einstein's theory will also tell you what it is. But first thing, it tells you that the distance is time dependent. Okay, so you no more expect a static universe. Okay, so how does universe expand? Einstein's theory will tell you, Einstein's theory of gravity will tell you that if I put some energy density in space, okay, the density value is rho. So every time I write rho, you know that it's energy per unit volume. Okay. So if I put energy density, it is going to be related to the velocity of this expansion, the scale factor. Okay. This A as a function of time, which I talked to you. You can think of it physically as some kind of a distance between any 2 points in space, or maybe 2 far away galaxies in space. Okay. And this distance is going to change. And that change, this A dot, is really induced by this density. More is the density, more is the A dot. Okay. This equation really doesn't tell you whether A dot is positive or negative. You can take a square root, you get both positive and negative, which means that it tells you universe can expand, it can contract. But if you put A dot equal to 0, then density has to be 0. So if you put matter in the universe cannot be static. It has to expand or contract. Okay. And this particular combination of A dot by A, is called Hubble parameter. Okay. So just remember, Hubble parameter is A dot by A. Let's go on. The acceleration of the scale factor. So this has to do with at what speed it expands. But the acceleration, whether it expands faster and faster or slower and slower, is actually depends on a negative sign into a combination of rho and pressure. Okay? It's rho plus 3 into pressure. So whatever matter you have, it has some pressure, it has some density, and a particular combination of it with a negative sign decides whether this expansion, suppose it's expanding initially, its expansion is going to slow down or it's going to speed up. Okay. Now, if you go to your Newtonian logic, you say, how can expansion speed up? Because if I have all these gas molecules and the universe starts expanding, but these molecules or atoms are pulling each other by gravity, so then it should slow down, right? It should not speed up. But as I told you, in Einstein's theory, gravity can be repulsive by the fact that pressure could be negative. If pressure is negative, this could be actually positive, and we'll discuss this in detail. So it's possible that the universe will accelerate, not just decelerate. When I say density here, what I mean is all sorts of density, whatever we have. We have atoms, we have light, we have neutrinos, dark matter, dark energy, and who knows what else is there in the universe. Okay, but these are definitely there. And so you have to put everything here, and that will make the universe expand. Okay. So the theory predicts that the universe must be expanding or contracting. Okay. Now it's up to observation to figure it out. And so Hubble did the observation and figured out that, okay, all the galaxies in the universe that he saw, faraway galaxies, are going away from each other. So universe is really expanding. That was a verification of Einstein's theory of gravity. So let's take these facts on their face value and let's run the logic forward. Okay, so universe is expanding today, great, and we have by this decade we know exactly how universe has been expanding for a long time, and I'll show you the graph. The scale factor, which I told you is sort of like the size of the universe as a function of time, has been expanding sort of like this. So initially, the scale factor was very small. We'll come back to it. Then it expanded and decelerated, and at the present it's accelerating. This acceleration is due to dark energy, which we are not talking today. So we'll ignore it and we'll just take the minimal information from this diagram, is that, okay, universe is expanding today, and in the past the scale factor was smaller. So any two points that are far away today, in the past they will be closer to each other. So what does that mean? That means in the past universe was denser and hence hotter. So it was hot and hot. Okay, so how long back can you trust this logic? Let's close our eye and say, okay, let's trust it all the way that we can think of. Okay, we'll reach eventually a point where the temperature of the universe would be greater than thousands of degrees. Let's say 3000 degrees. At 3000 degree, you can't have atoms. Now, electrons have so much of energy that they will get away from the nucleus. So universe will be a plasma. So all the protons and the electrons will be separate. Okay. So the full universe will be dense, extremely dense, and in a hot plasma phase. So it's something like the interior of our sun. The entire universe was like that. There were no galaxies, nothing. If this logic is correct. Now, how do you test it? Okay, you say universe was expanding. It is in the plasma state, hot and dense. As it expanded, it started to cool down. When it was very hot, what was happening is it's dense and it's plasma, so there are free electrons moving around. So photons, when they're trying to propagate at the speed of light, they will go and hit one electron, then move and hit another electron, then another electron. So they're not able to propagate much further in the universe. So the universe looks opaque, hazy. Okay, it looks very, very opaque. But as it expanded, it cooled down. So ultimately, the temperature dropped to a level where electrons now could combine with protons to form neutral atoms. The first atoms which were formed were actually hydrogen and helium, a little bit of lithium, but not the higher elements. Okay. So universe cooled down from the plasma phase to form hydrogen and helium. And we know that hydrogen and helium are transparent, not opaque. How do I know? For example, in this room, I have a lot of air molecules, but you can still see my face through the camera because light from my face could travel to the camera without any interruption because of this gas molecules. So universe became transparent eventually. So these photons started traveling. And before traveling, they were getting kicked. So they were in some kind of a thermal equilibrium. So they had a black body distribution before traveling. And then once universe became neutral atoms, neutral molecules, they started traveling freely. So you see a free black body radiation coming towards you. So you should see it for sure. And in fact, you can calculate what should be the temperature of the black body radiation today, because you know at what temperature neutral atoms should be formed from basically the ionization energy of hydrogen and helium. So you can calculate, and people predicted it should be something around minus 270 degrees Celsius, something around 3 Kelvin. Okay. So this was a prediction of this hot plasma expansion theory. This is what we call Big Bang. I'll come back to it in a while. And in 1965, this was detected. What was detected is that if you look in any direction in the sky, you see a black body radiation coming towards you. It's perfectly black body. It has a temperature around 3 Kelvin. Okay, and the measurement was rectified much. Like it was a much better measurement was taken in 1990s by Kobe, and I'm showing that measurement. Okay. What I'm plotting is the black body distribution. Here is the frequency of the light which comes, and here is the intensity, and you see that the solid line is a black body radiation, and these dots with bars, horizontal bars, are actually the data, and you see the match. So this is the most perfect black body radiation we know. We can't even create this good black body radiation in the lab. Secondly, the error bars here in the data has been increased by 400 times so that you can see the error bars. So it's that perfect that the actual error bars are actually 400 times smaller. Okay, so it's a perfect match. So we know, so from that day, we know for sure that our universe began at some kind of a hot, dense plasma phase. There were no galaxies, no neutral atoms, but there are all sorts of particles. Okay. And then it expanded and cooled down to form the today's universe. This is for sure is guaranteed. So this is the observationally verified fact. And you can actually do a sky survey. Since this light is coming from the universe itself, it should not be direction dependent. No? It should come from everywhere to you. So you can put a satellite in the sky, which can measure. By the way, this wavelength of this black body radiation peaks in microwave range. So this is called cosmic microwave background radiation. Okay. Background, why we know it's called microwave, because today it's coming as microwave. When it started, it was actually yeah, I would say yellow light. Okay, so it was an optical, but since universe is expanding, it got stretched and cooled down and became a microwave. Anyway, so if you do a sky map in all 360 degrees, then what you are going to get is a completely uniform map. Okay. Here the color actually tells you the intensity or the number of photons you get from different directions, and you see in each direction you get almost, in fact, almost exactly same number of photons. So it's perfect homogeneous radiation. Now, what does this tell you? This tells you that your universe was completely homogeneous, uniform in the early times when it was a plasma, because this light is coming from that plasma when that plasma became neutral atoms. Okay. So that thing also we know. We know our universe was extremely uniform, and it was in a hot dense plasma phase. Now this is a successful story, but this creates a big puzzle. The puzzle is what you see today. Okay, let let's go backwards. Let's see what happened. When this plasma cooled down, you saw hydrogen and helium gas, let's say, and this gas is absolutely uniformly distributed all everywhere in the universe, and universe is expanding, so this gas also expands and dilutes. So you have a completely uniform gas, expands and dilutes. So the gas will remain gas, and it will keep diluting and diluting and diluting, and you'll have a boring universe where nothing exists, just hydrogen and helium. But we don't have that boring universe. We have a universe where we see stars, galaxies, clusters, planets, even human beings. So this is not our universe. So something is missing in this picture. Since we see structure today, it can't be that the early universe was perfectly homogeneous. There has to be somewhere little higher density, little lower density. That has to be there. And then what would happen? You let gravity do its work. Wherever there is higher density, gravity will pull more and more. You remember in Einstein's theory, gravity depends on density. So if you have higher density, it will become higher and higher and higher. So it will take out matter from its surrounding and grow. And finally, the gas will get compressed and start to burn, nuclear burning, and then you'll get stars. Then there'll be galaxies and all sorts of structure. Okay. So what we predict again is that there should be some kind of non-uniformity, inhomogeneities in this map. Okay, but we have people tried and went. This is actually temperature map. Okay, you can think of intensity, but this is really temperature map. If you measure temperature in all directions, up to 4 digits, they come the same number. It's 2.7255 Kelvin. So people made better thermometers which can measure temperature up to 5th digit, and sure enough, they found the fluctuations. Okay. This is a modern map, Planck, but I'll show you the original map also later. This is a map from 2013, and what you see is not completely uniform temperature or intensity. You see there's fluctuation. And the difference between this, let's say this spot, let's call it a little hot spot, and this, which is a little cold spot, let's say, the difference between them is probably 0.00001 Kelvin. So they're almost uniform, but nevertheless, it's not fully uniform. And this much of fluctuation is enough to form structure, which is what I want to show you in a minute. So what will happen in the universe? Let's see. Universe was in some kind of hot and dense plasma state. It expanded. As it expanded, since universe is expanding, density of many objects are actually falling, apart from one object, which is dark energy. We'll not discuss it today. Density of photons are really falling faster, and density of atoms and dark matter are falling a little slower. So what happened? The early universe was full of radiation. It had dark matter, it had normal matter, but it was mostly radiation. Later, it made a transition to matter-dominated epoch, and today it is dark energy. This is out of our topic today. Okay. The same history is now shown in a diagram. Forget about what happened to the left of this diagram. So forget this. We'll come back to it. But we know it was in some kind of plasma all the way until this time. Okay, I'll show you what was the time also. After this time, there were these tiny fluctuations were amplified by gravity. And slowly they start to form some kind of wave structure. And today we have this universe with galaxies and planets and stars. This is the story. What is important in the story is, first thing, the transition happened from plasma to cold gas. Well, cold or hot, depends on your definition, plasma to neutral gas. And if there were no fluctuations, it was completely smooth, then today the universe would be completely hydrogen and helium. But there were fluctuations and we have detected them. And so today universe is filled with galaxies and clusters and all sorts of structure. Interesting universe. Okay. And we have found the fluctuations in this density. So if universe has an average density, then if we go from one point to another point, the overall fluctuation in density would be of the order of 10 to the power minus 5, or its square would be something like 10 to the power minus 9. Okay. Also observationally, we have how we have progressed. I want to show you because some of the people here are physicists. When we first detected these fluctuations in 1990s by Kobe satellite, the spots were really big. We didn't have better resolution. But then we went from Kobe to WMAP. The resolution became fantastic. Then finally WMAP to Planck, and we have amazing resolution of these fluctuations. Okay. So the temperature fluctuations are of the order of 10 to the power minus 5. Now you can test it, how structure in the universe formed, by starting from these fluctuations, very small fluctuations at some early time. So look here, this looks almost uniform, but there are some fluctuations. And then let it grow over gravity on its own. You don't do anything extra, just leave gravity. You have dark matter, normal matter, photons, everything, and you have gravity. Then it becomes a little clumpy after a while, then becomes even more clumpy after a while, and finally becomes this cosmic wave kind of structure. Okay. So we have verified this. So this is another success story. So we not only know overall how universe was behaving, we also know how these fluctuations were behaving. They were small and they got amplified by gravity and then formed galaxies. Okay, great. This whole story which I told you is called the Big Bang theory. Okay. There is no bang here. I didn't say any bang or any burst anywhere. So this is what Big Bang theory means. A plasma state of hot dense plasma state will cool down to form normal universe, and structures will grow from initial tiny fluctuations. Now we come to the heart of the topic. So we have seen initially these fluctuations were small, tiny, 10 to the power minus 5. So it took sort of millions of years for stars to form. Okay, great. The question is, this is Big Bang theory. The question is, there is some trouble with this Big Bang theory. And I'll tell you why. Observationally, there is no trouble. The trouble is, for this Big Bang theory to work in a nice way, when this initial state, wherever we're starting with some plasma with some fluctuations, right? This state is extremely unnatural if you trust Einstein's theory. Einstein's theory says you should not have started from this kind of a phase. I'll tell you why. First thing is, what we see is the entire universe is almost smooth. Okay. If you apply Einstein's theory to the entire universe, it should be smooth only over 1 degree sky. So if I see the sky only over 1 degree, it should be smooth. But I'm seeing entire 360 degrees smooth. So this is the first problem, which is horizon problem. The second problem has to do with curvature of space. In Einstein's theory, space can be curved, and it also tells you the curvature increases with time. Okay. So that means if I take a big triangle in the early universe and sum all the angles, and I get, let's say, 180.1 degree, just a little bit deviated from 180. Right, today, it should have become 10 to the power 20 degrees or something. So it should be an extremely curved triangle. But we don't see that. What we see today is 180.000 degrees. If you add all the angles of a triangle, this is unnatural. So you have to start with 180.20 zeros, so that today you have 180.3 zeros. Okay, this is an unnatural problem. Similarly, there are some other problems which I'll not go into for this talk. We may come back a little later. There are many other problems. These problems, they don't indicate that Big Bang theory is wrong. It just says that initially something funny was happening in the Big Bang theory. And it turns out all these problems, not one by one, all the problems in one blow can be solved if you assume that your universe has not been expanding and decelerating, but initially, before this hot Big Bang plasma phase, there was some time when our universe sort of inflated or accelerated for a while, just for less than a second, a fraction of a second. It inflated, accelerated, then it started decelerating. Okay. This is the only hypothesis we're going to take. So since universe has to accelerate, we need some kind of repulsive gravity, all right? And it has to accelerate prior to when it was 1 second old. Why? Because we know it's how our universe has been expanding from 1 second up to today, which is 13.8 billion years. Okay. So before that time, something should have happened which made these funny initial conditions for Big Bang. We are going to call that phase, that rapid, short, accelerated expansion, as a cosmic inflation, sort of like inflating something. Okay, great. This will set the initial conditions to be natural. So before we proceed to inflation, for next 10 to 15 minutes, I would like to just for 1 minute show you the overall timeline so that you know where we are. Okay. Starting from here, which is about 10 to the power minus 10 second, till today, which is 13.8 billion years. So from 10 to the power minus 10 second to 13.8 billion years, we have fairly a good idea about what was happening in the universe. Okay. The first atomic nuclei, it's called Big Bang nucleosynthesis, were formed. Only hydrogen and helium and a little bit of lithium were formed when the universe was 3 minutes old. And then I told you universe was initially a lot of radiation and then became matter. So that happened about a time when universe was 60,000 years old. Then these first neutral atoms formed when it was about 4 lakh years old, so 400,000. This is the time when the light, this cosmic microwave background light, which I'm going to keep calling as CMB. Okay, so the CMB light has already started traveling by this time. And then stars formed and universe became dark energy dominated, and this is today's universe, 13.8 billion years. Fine. So something must have happened before this, which set the funny initial conditions for Big Bang. And that's what we are calling a cosmic inflation. So we are really going to sub-fraction of a time when universe was less than a fraction. You see the kind of temperatures we are talking about. We're talking about 10 to the power 16 Kelvin. You can't test this in lab. Our maximum temperature probed in lab is sort of like this, a little bit higher than this, a couple of orders higher than this. That's it. And there's some mistake. It's greater than this. So it's much greater than 10 to the power. It should be 17. It's much greater than 10 to the power 17 Kelvin. In fact, the kind of temperature we usually talk is about 10 to the power 25 Kelvin or even higher. So we're going to that kind of physics now. Okay. So what is cosmic inflation? It has to be a period of accelerated expansion, which was transient. Means it didn't last forever. It was a short period. Because if it lasts forever, then we'll not see today's universe. It'll all be accelerating. We don't see that. Second, this should have happened before this hot Big Bang phase, before 1 second, much before 1 second. And as I told you before, in Einstein's theory, acceleration you can have acceleration or repulsive gravity if rho plus 3p is negative. Okay. So for acceleration, you need rho plus 3p is negative. Now energy density is always positive. It's the density of energy. So pressure has to be negative. So what you need is some kind of matter which when you smooth out everywhere in the universe, it has a negative pressure. Okay. So we need universe to be temporarily filled with negative pressure substance, not forever. So it will be negative pressure substance. After a while, this substance will decay away. So it's some kind of a radioactive substance. It will go away, and then it will form normal electrons, protons, photons, neutrinos, dark matter, all the stuff. Okay, this is the setting of inflation, cosmic inflation. These things might seem a little esoteric, but these are all some of the features of this theory has been observationally verified, which I'll show you in 5 minutes. So universe need, and by the way, we have to solve all this problem. Why it is so smooth over 360-degree angle, not 1 degree angle? Why is it so flat? Like why is it so close to 180 degrees if you are the 3 angles of a triangle? Well, to solve all these problems, you need this inflation to expand universe by a factor of e to the power 60 times. Now imagine, you have less than a second, much less than a second. Now within much less than a second, within a fraction of a second, our universe has to expand by e to the power 60 times. Okay, so that is why it is called inflation, not just any acceleration. Okay, it's really inflated. And then it solves all the problem. Great. We call this language e to the power 60 times as 60 e foldings. So if you ever go to a talk and you listen always e foldings, this is what they mean, e to the power 60. Fine. Essential things required. First thing, a negative pressure substance, which was filling our universe at that time. Let's call it the inflaton field. It inflates the universe, so inflaton field. Second thing is it should be transient, so it should go away, decay away. So it should make the universe a transition from an accelerated phase to a normal hot Big Bang decelerated phase. Then it must decay away after the end of inflation, and it should create all the matter that we see today. Why? Because if I expand the universe by e to the power 60 times, whatever density I had gets so much diluted that I have almost no matter in the universe. Okay. I don't want that. I see the early universe is hot and dense. I need dense universe. So when it decays away, it should give its energy to normal matter. So it should sprout out particles. So you can think of all the particles, all the protons in your body were actually created in this process. Okay, sometime back when universe was less than a second old. Great. This process is called reheating, about which we are not going to discuss much. Then begins the good old, observationally verified, hot, dense plasma phase, or the standard Big Bang theory starts. So inflation first, then the standard Big Bang phase. Now, how do we achieve that? We need all these things to happen. Well, it turns out you can achieve it very simply. In fact, when Alan Guth first stumbled upon inflation, he was not trying to discover inflation. He was working on something called a scalar field, and he saw it can inflate the universe and solve all these problems. Okay. So what is the scalar field? This is again a very simple thing. This is some kind of a field, like temperature is a field. A field is something which permeates everywhere, like electric field. It's everywhere. So the scalar field is everywhere. At least at that time when inflation was happening, the scalar field has energy density, which is comprising of two terms. The first term is actually a kinetic energy of the field. So it has to do with how fast the field rolls down. The second term is the potential energy of the field. So there is a height. Okay? The total energy density is coming from a motional term and a height term. Okay? The combination is the total density. And the pressure is a negative sign in between. So it's kinetic energy minus potential energy. Great. Now, what do we want? In Einstein's theory, first thing we want, the way universe expands depends on what kind of density is there. So it depends on the combination of kinetic and potential. And the way universe accelerates depends on the combination of rho and pressure. So if you take rho and pressure and figure out when it should accelerate, you get a fantastic condition. The condition is very simple. Its velocity should be less than potential. Okay, that's it. All you want is a scalar field. It permeates the universe. This field is not very esoteric because we have discovered a scalar field in lab. It's called Higgs boson, so something like that, which fills the universe. And but it's rolling down slowly, okay, across its potential. As long as the height is much higher than the velocity, you get inflation. This is the condition for inflation. It turns out, you would think, just think for a while, you want it to roll down slowly, right? For it to roll down slowly, you cannot make it very steep. If you make it a steep potential, it will roll down faster. But that's not required. The reason is the following. How a scalar field rolls down a potential in a universe, expanding universe, is basically something like simple harmonic oscillator. So it has an accelerated term and some kind of a force term, which is pulling it towards the center, which is the gradient of the potential. Okay, it's pulling it towards the center. But there is a friction term. It is slowing down because of the expansion of the universe. So expansion of the universe is taking away some energy, some kinetic energy from this field. So if the expansion of the universe is high at early times, then it could be really a heavy friction. So even if it's a steep potential, the friction is high enough to keep it almost at rest. Okay, so it moves very, very slowly. And we technically call it slow roll inflation. It will roll slowly. So for a generic potential, even for a sort of steep potential, it's going to roll slowly and inflate the universe. Okay? This is the mechanism by which we'll have this accelerated expansion. But we also want it to be transient, so it should end somewhere. Great. So the potential actually has a minimum, so it turns down. So it becomes really, really steep. And as universe expands, this friction term is also going down a bit. So the net result would be that there will be some point where it makes a transition from a slowly moving object to a rapidly moving object. That ends the inflation, because for inflation we want it to move slowly. That's it. So you have inflation early times naturally, and then end of inflation naturally. Third thing we want is reheating. Reheating means it should sprout out all the standard model particles, all the normal particles. It does that also. There is a mechanism which we are not discussing today. We'll come back to it maybe if there's a question. Okay, so we have got it, but there is still a problem. The problem is we have achieved inflation. We have achieved what we wanted. It sets the initial conditions for the Big Bang. Fantastic. But the problem is, since it makes the universe expand e to the power 60 times, it makes universe absolutely smooth. So smooth that temperature everywhere should be same up to many decimal places. But we don't see that. We see some tiny fluctuations, which is essential for the structure in our universe. So what happened to these fluctuations? Inflation would just wipe them out. Can inflation help? It has helped us to solve all the problems of Big Bang, but can it help us to solve these fluctuations? It seems to be not solving it. It seems to be creating the problem, but no. Lightning strikes again, and it solves it. It can solve it, and it does necessarily solves it. It necessarily creates these initial fluctuations via quantum mechanics. Now we are in the early universe where temperatures are so high that it's extremely quantum mechanical universe. And I'm going to tell you in brief how quantum mechanics produces these fluctuations at the end of inflation. Okay, great. So I told you the story that this field was slowly rolling initially, and then somewhere inflation ended, then it oscillated, and it was reheating the universe after that. But when it was rolling down this smoothly, classically, quantum mechanically it cannot. It has to fluctuate from place to place. So classically, everywhere in the universe, the inflaton field will be at the same place. But quantum mechanically, it's not. Somewhere in the universe, the field will be little down, the potential, somewhere it will be little up. So wherever it is down, little down, the inflation will end sooner. So the hot Big Bang phase will start sooner there. But wherever it is little up, the hot Big Bang phase will start little later. Okay. Now during inflation, the density doesn't dilute much, so it's almost constant density. But during hot Big Bang, since universe expands in a way that density falls, so what happens is that those places in space where you create hot Big Bang material like electrons, protons, all this stuff, their density has started decreasing. Then somewhere else the material is created, new material is created, but that has little higher density. So since the end of inflation fluctuates from space to space, the density of matter after a while, when inflation is over almost everywhere in the universe, density of matter will also be different. This creates the quantum fluctuations, initial conditions. So basically, overall, there is the value of the field everywhere in the universe has an average value, but then there is some tiny fluctuation, somewhere a little higher, somewhere a little lower. This creates a delay in the end of inflation from place to place, and hence fluctuations are created. But this is just a qualitative statement. I'll quantify it, that it creates a particular type of fluctuation, and we can observe and measure it and check if it is correct or not. I will not have, if this was a lecture, like a classroom lecture, I would have taught you how exactly quantum mechanics works and it solves. But I want to stress you, especially people who are in masters and doing physics, this is one of the most beautiful applications of quantum mechanics. It is much more important than hydrogen atom, because it forms all the structure in the universe. So our existence depends on that. And here's a quote from Juan Maldacena, which you can read much later in a school where I was there. And he said, this is the most important calculation every physicist should know. So I cannot stress how important it is. Okay, we're almost at the end. I'll show you a little bit of mathematics. So what is fluctuation? Think of any random curve. Okay. You can write a random curve as some amplitude times sine x plus some other amplitude times sine 2x plus some amplitude times sine 3x. So basically Fourier transformation. Okay. So since inflation creates quantum fluctuations, we can think of it as it has many kind of waves with different amplitudes. Okay. So amplitude for a given wave number or frequency or wavelength, whatever you call, for a given wave number, let's call the amplitude to be AK. Einstein's theory dictates that this AK, how it changes with time. You can calculate this AK. It turns out the AK also satisfies a simple harmonic oscillator. You see how many times simple harmonic oscillator is popping up, right? So you see a simple harmonic oscillator from here. So this is basically a simple harmonic oscillator term, but you do have a friction again, but this time very different. This time the friction term, which is given by A into Hubble, A is exponentially expanding. Universe is exponentially expanding during inflation. So the friction term here is not going down but going up. It's exponentially expanding. So what would happen? Initially, if the friction is small, you have an oscillator which is oscillating. Okay, so the amplitude as a function of time is oscillating. But then friction becomes so heavy that this term has no meaning and it's heavily friction dependent. You can solve this equation. Do it as homework. Solve this equation. What you're going to see is that it's going to get stuck somewhere. It's very similar to you have some kind of a container and you pour some honey, dense honey inside it, and let a ball roll up and down. Suppose the density of the honey is increasing. After a while, the ball will stop oscillating and it will be stuck somewhere at some height. Okay, that's what happens. And the amplitude of quantum fluctuations, the amplitude of or the standard deviation. So on an average, there is no fluctuation. So everywhere the field value should be same or density should be same. But quantum mechanics says no, it changes from place to place. So square of that amplitude is called power spectrum. Is really dependent on square of this AK which I'm talking about. And you can calculate everything from physics. It turns out it depends on how slow it is rolling down. The slower it is rolling down, the higher is the amplitude of fluctuation, and the faster it is rolling down, the lower is the amplitude. Okay, so it creates some kind of a pattern of fluctuations, and this pattern is a prediction which I can't show you in a short time, but I'll just show you the graph how this pattern has been measured. So when you see at these fluctuations, this temperature or density fluctuations, this is an observationally taken photograph by Planck 2018. You just see spots, random spots. Now, how do you quantify it? What you calculate is at a given, how many 1 degree spots are there, how many 2 degree spots are there, how many 3 degree spots are there, something like that. Okay. So if you calculate that and plot how many of them are there as a function of their angular size, what you are going to get, this is a big angular size and this is a small angular size. Okay, you see that number sort of oscillates. Okay, so there's a pattern to how it should be, and the green line here is the prediction by inflation, while the red dots are the data, and you can see the match. Okay, so these are predictions of inflation which have been verified by observation. But inflation also predicts gravitational waves. For that, I have to go to a different place. Yes. So first thing I showed you, it creates these density fluctuations or temperature fluctuations. They have been tested. It creates a particular pattern. The pattern is almost fractal-like in the sense that all waves, in the sense that all waves have same wave number, same amplitude, but there is a little difference. The difference is that those waves which have large wavelength have little larger amplitude, and those which have small wavelength have smaller amplitude. And that thing is usually indicated by something called NS. For now, it's just a number. I'm not defining it, but that has also been verified. Okay, that this NS should be less than 1, but should be very close to 1, and it does. What remains? Yes, so there have been many observational missions, right from the discovery of this cosmic microwave background radiation, related to a Nobel Prize, all the way from 3 generations of cosmic microwave detectors to Planck. And we are very sure that all the density fluctuation predictions have been tested. But and this is the progress, that from some hazy detection to a very, very solid detection. But you want to the next prediction is gravitational waves. So in this quantum mechanics during inflation not only creates density fluctuations and temperature fluctuations, also creates metric fluctuations. It also fluctuates distance between 2 points, and that creates gravitational waves. And this also has a pattern. Like the density fit into some oscillatory pattern, the gravitational waves have a different kind of pattern, and that can also be tested. We are looking for it now. There's a new mission which has been granted, and this will be a big deal, and it involves lots of theoretical work, computation, instrument, data, and all sorts of stuff. Then inflation has some relation to multiverse and eternal inflation, which are very exciting topics to study. And the question is whether they can be tested or not. People are now trying to find out if we can test them. The quantum mechanics during inflation actually creates multiverses. If there's a question about it, I'll answer, but otherwise I'll skip. This is Alan Guth, Andre Linde, and this is Paul Steinhardt. They worked on inflation early times in the US and Russia, and they got the Dirac Medal in 2002, as well as Fundamental Physics Prize, two of them. And last year, Alexei Starobinsky and Mukhanov and these two people, they won Dirac Medal for inflation, as well as this person, Sunyaev, got it for this CMB fluctuations. Okay. Just to mention. I would like to end my talk by giving you some concluding remarks or take home message. The first thing is the Big Bang theory means expanding hot dense plasma which cool down to form the present universe. There is no bang, no singularity in the theory. We don't talk. The theory doesn't say anything about singularity or bangs. The presence of CMB radiation has been predicted and detected and verified. Then the structure of the universe, we also know how the structure formed. It formed from gravitational amplification of these tiny density fluctuations, which were there initially. But the initial conditions for Big Bang are unnatural unless there is an inflationary or accelerating phase prior to that. So we proposed that, then we made some predictions about this inflationary theory, and the density predictions have been tested up to very large precision. And we are waiting for gravitational waves. And this will not only verify that inflation happened, it will also tell you what kind of physics was going on at that energy scale, which you cannot prove by, let's say, Large Hadron Collider or any other machine on Earth. So thank you very much.
Thank you so much. That was really informative. And we have a whole bunch of questions coming in from a lot of our students. So before we get into that, personally, I would like to, just ask you if you would like to comment on, being someone so involved in standard cosmology and inflationary theory. Do you personally feel there are any strong loopholes right now which gets opposition from maybe other theorists? And do you find any weaknesses in inflationary theory at all?
Oh, fantastic question. For standard model, standard Big Bang theory, it's very difficult to find a loophole. There are some small tensions, but they will not break down the full picture. They're going to, maybe you have to add something a little bit. For example, there is a tension called Hubble tension. You measure the Hubble constant by two different ways and match them, they don't match. So there seems to be some paradox. But it's not going to break down the Big Bang picture, Big Bang theory. There are some other puzzle has to do with how early structure can grow in Big Bang theory. Okay. I told you this initial fluctuation, they have to grow by gravity. It turns out the growth, what we observe, is a little faster than what it should be. So there are these tensions in the Big Bang theory. Now coming back to inflation, inflation is not a verified theory fully. Big Bang is a verified theory, that hot plasma became universe. Inflation came before that. We have indirect predictions of inflation that we test. So it could be possible that inflation is not correct, something else is correct. For example, another alternative is that there was no inflation before Big Bang. Universe was contracting, then bounced back and expanded. That's also possible. But we cannot calculate things very definitely in this picture. What happens at bounce, we don't know. There are things which become infinite. Plus, inflation is the most minimal way you can do. You can solve all the problems, and you can solve all the problems. That's the point. It's not like it's not a hocus pocus where you adjust one screw and solve one problem, but another screw gets distorted. That doesn't happen here. You say inflation happens, all problems solved. Plus, it is a natural scenario in the early universe. So theoretically, it's in the, I would say, I would bet it is probably correct, but ultimately observation should decide. So,
what kind of evidential support would verify inflation for sure?
Gravitational waves. Let's say we have measured the amplitude of these density fluctuations. If the amplitude of gravitational waves would be within 3-4 orders of this density fluctuations. It will be a telltale signature that inflation. So,
Okay.
yes.
So we have Ayush here who has a question about primordial black holes. So can we have Ayush? Yeah.
Hi.
Thank you for the lecture, sir. So my question was about uh, primordial black holes. So in the seminal paper of 2015 about the discovery of gravitational waves, the authors were mentioning the need for characterization of the gravitational wave background. So in your opinion, what is the contribution made by the primordial black holes, and how does it compare to the contribution made by the astrophysical black holes? Is there any way to constrain the amount contributed by each?
Okay, great. Got your question. So I'm first going to answer in a word and then going to elaborate. Answer is nobody knows. Okay. So let me elaborate why I said so. We are sure that there are binary black holes in the universe. We've seen gravitational waves, right? And we don't know whether these black holes are astrophysical or primordial. Now, I also didn't discuss what is primordial, so let me tell it for the viewers. A primordial black hole is a black hole which is not formed because of death of a star, but it is formed in the early universe from the plasma. So it's not like there's a star initially and then the star collapses and then forms a black hole. We have the hot dense plasma. I told you the fluctuations are tiny, right? Tiny fluctuations. But it's possible that at very small scales, very small length scales, these fluctuations are not tiny. They are actually very heavy fluctuations. That means somewhere you have a very large density compression. It's a compression. So then no pressure can save it. So the whole plasma will just collapse. That part of the plasma will collapse and form a tiny black hole. You can form that. That's primordial black hole. Today we know for sure that 10 to 100 solar mass black hole binaries are there in the universe from gravitational waves observation, also from X-ray binaries and stuff. But we don't know whether they are primordial or not. So if there are primordial black holes, suppose, and they rotate around each other and then they merge and give out gravitational waves, right? This is what you are asking. So if I see the gravitational waves, how would I tell if they are primordial or not? One way to, it's not 100% guarantee, but it's an indication that when two primordial black holes come together and collide, and you analyze their gravitational waves, there is something called effective spin, which is related to the spin orientation of the earlier two black holes. Okay, and it's weighted by their mass. So it's like m1s1 plus m2s2 by m1 plus m2. That quantity in a primordial black hole would usually be very, very small. In fact, close to zero. And in fact, I think apart from one observation, almost all observations have very close to zero. So that's an indication of primordial black hole. For astrophysical, it could be zero. In a, how to say, it's not most probable to be zero, but in a lucky chance, it could be zero. But mostly we would think it should not be zero. So that's one way of knowing. There's a second thing. The second thing is when you produce primordial black holes, you need at small length scales heavy fluctuations. And I told you when you create density fluctuations, you also create gravitational wave fluctuations. So just by their existence of primordial black holes, you will also have a gravitational waves in the early universe. Not by their mergers, even before that, just because of their existence. So there will be some other gravitational waves which have a different nature. Okay. They will not be gravitational waves from two binary black holes, but an overall stochastic background gravitational waves. So yes, so if you see that, then probably there are primordial black holes. Okay, and this the wavelength at which you see these gravitational waves is different from the wavelength that I was talking about for cosmic microwave background fluctuations. Okay, so these are small scale fluctuations. So I can tell you, for example, this could be millihertz gravitational waves, okay, or maybe microhertz gravitational waves. So yes, there is a way to do it, but nobody knows how much is. We don't know. It just started. Gravitational waves physics just started 3 years back, 4 years back.
Okay, thank you, Ayush. We have Vikrant who has a question about dark matter. So let's.
Hey, am I audible?
Hi. Yes.
Yeah. So, since we know that around 23% of the universe is approximately dark matter, and little research would tell us that they're classified as hot dark matter and cold dark matter. So, my question was, how is regular dark matter different from the other types, especially cold dark matter, and why does it make a difference? And part two would be is the part two of the question is what was the motive behind the lambda CDM model, and if there's any correlations with primordial black holes.
Thank you. Great question. So, to explain quite a lot now. First thing, what is a dark matter? It is dark in the sense that it doesn't interact with light. Okay, but the word dark can be a little misleading. Now, suppose I have an object which absorbs light but doesn't emit. It will also look black or dark to me, right? Let's say like a black hole. That's not a dark matter. Dark matter neither absorbs nor emits. Or if it does absorb and emit, it's so low that we can detect it. We are not able to detect it. It's so low. So its interaction with light is very low. So it's almost like a transparent matter. In some sense, it is not very mysterious. I'll tell you why. In this room, if I want to talk to my mother on phone, I can just call her up, right? But there are walls here. So how is it that there are walls, but still these microwaves or radio waves, whatever I'm using in my phone, are penetrating these walls? So for this wall, for radio waves, the wall is a dark matter. The radio wave passes right through it without interacting, right? But for photons, optical photons, it is not a dark matter because optical photons cannot pass through a wall, cement wall. Okay, so you see, so what dark matter means is how it interacts. So if I have a dark matter and light, I'll make them cross through each other. They'll just cross. There will be not much heating or some reflection, no scattering, nothing is going on. This is a dark matter. Okay. Second thing, what is cold, hot, and there's also called something warm dark matter. It has to do with, well, I'll try to explain it not too technically. It has to do with, suppose I have a dark matter at a given temperature. If it is oscillating, if it has a kinetic energy or velocity dispersion, if that is very high or very low. So if the dark matter is extremely massive, it has a large mass, so then it will not move much. Its most energy is coming from its mass, not from its velocity dispersion. So that's a cold dark matter. A cold dark matter will not collide with each other in some sense. So they will not create pressure. They don't have a pressure. So they have energy momentum tensor, in the sense they have energy, they have momentum, they have everything, but they don't have pressure. They're almost pressureless. And I've been telling you in Einstein's equation, expansion depends on pressure. So since these guys don't have pressure, they are cold. We call them cold dark matter. A hot dark matter would have some pressure. So that's why they are hot dark matter. Then he asked me about what is actual dark matter. Actual dark matter means you asked me whether the dark matter in our universe is cold or hot. It is actually cold. So that's why we call it CDM. Okay, cold in the sense that it is pressureless. It behaves as if it doesn't have pressure. Okay. So lambda CDM means your universe has normal atoms and photon and neutrinos and stuff. On top of that, you have dark energy, which is constant in density. Even though universe is expanding, dark energy has a constant density. That's lambda. Then universe has cold dark matter. It has dark matter, 27% dark matter. But this dark matter is cold, they don't have pressure. So the way they make universe expand is like a pressureless substance. Okay, so that's a cold dark matter. You can roughly think a very heavy dark matter would usually be cold, and a very light dark matter would usually be hot. If the dark matter is a classical particle. And there is something called fuzzy dark matter, which is quantum mechanical. It is light, but it is also cold. That's a separate topic.
Okay. Yeah, that's really interesting because I think we often don't understand the different types. So yeah, we have Vivek Gautam who has a question about cosmology in general. Is he here? Is Vivek over there? Okay, let's maybe move to the next question by Ankita. Is Ankita there? Okay, yeah.
Yeah, hello.
Hi.
Thanks for the great talk. My question is, as a cosmologist, how do you make such precise theoretical calculations to estimate the percentage of hydrogen and helium, and also to develop theories of nucleogenesis?
Oh, great. Okay. So I'll first make a statement about all the calculations before coming to nucleosynthesis. We have a theory of gravity, which is Einstein's theory. It is telling us how space is expanding. Okay? So that actually dictates what kind of temperature is there in the universe. So if I create a hot gas, something in the universe, the expansion will make it cooler and cooler. Okay? And it also tells me what kind of energy density is there, because the Hubble parameter square is basically energy density. So by measuring the expansion rate of the universe, I can weigh the universe. And that's how I know this much percentage of dark matter, that much percentage of dark energy, because I can weigh it by measuring the expansion rate. Okay. So gravity helps in that. So gravity tells us what kind of density, what kind of pressure is there in the universe. Great. So we have some matter in the universe. Let's think of it as some kind of a gas, and it has. I know its pressure and I know its temperature and all that. So I can apply thermodynamics, for example, and study the system. This is one example. Second thing is particle physics or nuclear physics. In particle physics or nuclear physics, what happens? I have two particles. They interact for a while, then they go back, and their momentum changes. And this is what Large Hadron Collider measures. Okay. How much is the change in momentum because of two beam collisions? Okay. In the universe, same thing would happen in the early times because it's hot and dense, so all sorts of particles are interacting. But there are two things going on. The particles are interacting by some rate. They have some internal rate of interaction because of their particle physics nature. Let it be electromagnetic interaction or strong interaction, nuclear interaction. At the same time, they are being pushed apart from each other because of expansion of the space. So there is a tug war going on between them. As long as the interaction rate is faster than expansion rate of the universe, they will interact strongly. They will very nicely interact, and all the things that we know in laboratory physics, nuclear physics, particle physics will hold. But if their rate of interaction is lower than expansion rate of the universe, then they will not interact at all. So they will behave like non-interacting objects, which are being pushed apart because of gravity, okay, because of expansion of the universe. So basically, depending on which range I am, if I'm in the expansion dominated phase, I will use Einstein's theory to understand it. And if I'm in the interaction dominated phase, I'll use particle physics or nuclear physics. So in the early times, around when universe was about a minute old, at that time nucleosynthesis started. So a proton and another proton would probably snap, and something would happen. It's a complicated process, goes through different, deuterium is formed and stuff. But you can exactly apply the same laboratory physics. You don't need to know anything about gravity. The reason is because they're interacting very fast at that time, and space is not able to throw them away. Okay. So how can I do it as a cosmologist? I can do it because I have to use the exact nuclear physics that people use in laboratory physics. Okay, so that's how we can calculate. And if you do the calculation, you can figure out how much. Okay, so there is one point. there's a point where transition happens, that you go from an interacting phase to a non-interacting phase. Once you go to the non-interacting phase, you don't form any more nuclei. You don't form helium anymore. Okay, because the protons are not able to combine and form helium. So you know where it happens. And it happens exactly when the rate of expansion, Hubble, becomes equal to the rate of, let's say, nuclear process, nuclear fusion. So you know when it stopped. So then you can calculate exactly how much helium was formed compared to hydrogen. So that's how.
Okay, so the next question is about baryogenesis. So can you comment on maybe existing hypotheses that can probably explain the asymmetry of the amount of matter versus antimatter, and why that asymmetry might have been caused at such early stages of the universe?
Okay, first I'll make some general statements before coming to a particular model. What do we need for baryogenesis? in standard model of particle physics, you don't have baryogenesis. Baryogenesis means, okay, let me first put the question. The question is about why do we see so many matter in the universe, almost 100%, and no antimatter at all? Why is it? If you have done a course on quantum physics, it tells you that, okay, if I have a particle, I should have an antiparticle. There's a symmetry between them. But in the universe, I don't see an antimatter galaxy or something. You might have read it about it in science fiction, but not in the universe. We have never seen a star which is antiprotons. Okay, why is it so? So we have an idea how it could have happened. Initially in the universe, at early times, very early times, after inflation, but before the laboratory physics. So after inflation, but before 1 second. Okay. By that time, in that time, there is some process which violates this matter-antimatter asymmetry. So it creates in every 10 to the power 10 electrons or protons, it creates 10 to the power 10 minus 1 antiprotons. I'm saying this is necessary to explain what we see. First thing this should happen. So what will happen? I have this plasma interacting. I have in every 10 to the power 10 antiprotons, 1 extra proton. So when proton and antiproton mix, they will make light. Okay. Matter-antimatter will annihilate and make light, but one of the protons will be left over. Fine. But in the early universe, the energy of this light is so high that even light can create protons and antiprotons itself. Proton and antiproton can mix and form light, and light, when they meet, it's a dense medium. Light also meet each other, and they will form proton and antiproton. So you would still end up with having both proton and antiproton, even though proton is a little higher. Okay. So just having extra proton is not helping. What you need is out of equilibrium. Means the rate of forward reaction is not the same as rate of backward reaction. So when you form light, it's not that all of the light will again form back protons and antiprotons. That is required. So that is more probability for proton and antiproton to deplete to light. Then one of the protons will be left at the end. Okay. And that is the proton you see today. In every 10 to the power 10, one will be left. Okay. And we have 10 to the power 80 protons. So this is one thing should happen. Next thing. Did I leave any other criteria? These are called Sakharov criteria, by the way. He was the first guy, a Russian physicist, who figured out what all is required to explain the matter-antimatter asymmetry. So these things are required. How to achieve it? It has to be beyond standard model physics. Okay. The particle physics that you study, electromagnetic interaction, strong interaction, and weak interaction, they don't violate baryon number conservation. Okay. So you need something which violates this. Particularly what you have to violate is something called CP symmetry. You have to violate it. So you need some kind of interaction which should do it. So it should be beyond standard model, something new. And people have come up with several new ways to do it. One of the way could be a proton decay. We never see a proton decaying, right? It would be a disaster. Our body is mostly protons. Okay. If it decays, it will not exist. Okay, atoms cannot exist. But there's a theory which says proton decays over a very long scale, age of the universe, much higher than age of the universe. There, what can happen is you had a proton and now you don't have a proton. Baryon number changes, for example. Okay. This particular theory is ruled out. It's called SU5 theory. SU5 grand unified theory is ruled out. But there are many other ways to do it. There is a way to do it in standard model in a cranky way. It's a complicated. I can't explain it. It's a little complicated. It's called electroweak baryogenesis. Then there is baryogenesis through leptogenesis. But there are several models. They all go beyond the physics that we know. So they're all hypotheses. Okay. But we know the general criteria, what they should satisfy.
Okay, so from our YouTube comments, we have Suchetan, and he's saying, if right now we are having accelerated expansion, then how can you explain something like the big crunch theory, where we can expect the universe to fall back into a big crunch, and what could drive that process? Is his question.
Yeah, so I will correct the question a little bit before answering. It's not a theory called big crunch theory. Big crunch is an event which may happen in the future. Okay, so it's just an event. Just like universe is accelerating right now, it's not a theory, it's an event which is happening in the universe. Right? Universe is accelerating. Big crunch has to do with the fact. Suppose we forget about all acceleration. Let's stick to good old attractive Newtonian gravity. Now, suppose we start the universe to expand. So it's expanding, expanding, expanding. Because of attractive gravity, it should slow down, right? Okay. Now, if the initial speed was low enough, then it will slow down very quickly, and then it will turn back because of attraction. So it will turn back and collide. This thing is called big crunch. So the scale factor of the universe will increase for a while and then decrease down to zero. So it will expand and then contract back. This is what happens when you toss a coin. Okay, so if I have this car and I just toss it, it will go in the air for a while, it will stop and come back, right? This coming back again is the big crunch. This will happen depending on at what speed I throw. If I throw it at a speed which is greater than the escape velocity, it's not going to come back. Okay, if I throw this car with speed greater than 11 kilometers per second, it's not going to come back. So big crunch is not guaranteed. It's one of the future of the universe, one possible future. That would happen only if the initial speed was low. So that will go and stop and come back. It turns out for our universe, the initial speed was exactly the escape speed. This is the unnatural initial condition for Big Bang that I was talking about. The speed is such that it's almost in the escape velocity, not larger, not smaller. And what makes it that speed is basically inflation, sort of. So it's probably not going to come back ever. Plus, on top of that, today we have dark energy which has started accelerating it. So I tossed this car. Okay, it started slowing down as it went up. After a while, it started speeding up. So we don't have the hope of big crunch. So it doesn't seem that we'll have a big crunch for our universe.
Okay, is Aditya here? Does he have a question? Okay, Aditya is one of our youngest students in the astronomy course. I think he's 14 years old. So let's hear from him. You have to unmute yourself, Aditya. Hello? Okay. Yeah, so Vikrant, there was another question that you wanted to ask. So maybe you can add Vikrant. Yeah.
Hello.
Yeah, we can hear you.
Sorry.
We can't hear you now. Yeah,
Yeah.
you're inaudible. Can you unmute and mute and unmute again?
I think it's a mic problem. Can you speak without your earphones? I think now I can hear. It's a mic problem.
All right. So my question was more about the singularities that we encounter, and more like the failure of the Einstein's gravity, and how cosmologists deal with that.
It's a great question. Let's stick to the term bang in Big Bang. People, I said we are seeing that universe is expanding, and you can extrapolate back and see that it was hotter and denser. It was a leap of faith that I took. Not I, Georges Lemaitre and Friedman, all those guys, George Gamow, they took it. And they turned out to be correct. So they went back some time back and they said it should be plasma, and it was really a plasma. So great. So then the question is, can we just keep pushing it back and back in time? What would happen? Suppose I close my eye, I believe my theory completely, I keep going back. There will be a time t equal to 0 where I will hit singularity. I will hit a equal to 0. So all the density temperature would become infinite. Okay. So the point, is it correct? Was it really there, the singularity? The point is, it depends on what is the energy scale of the universe. When George Gamow extrapolated the present Hubble expansion to the early plasma phase, the temperature of the plasma phase is about a few thousand degrees. So it is electron volt scale energy, atomic physics. So he trusted all his calculations. When people did nucleosynthesis, again George Gamow, it was mega electron volt, sorry. And that is just nuclear physics we know in lab, so he trusted it. If you keep pushing it, you will ultimately hit some energy called Planck energy. Okay, Planck energy is the energy where Einstein's theory of gravity breaks down. So you can't trust it. You cannot. And every time there has been a singularity in physics, in a classical physics, has always been removed by quantum physics. So if you study a quantum theory of gravity, it will probably be ruled out. Okay. This is the general answer everybody gives. But I'll give you another answer which will satisfy even more. If you had gone this George Gamow way, all the way back and back and back, you would see universe will go from matter domination to radiation domination in past, all the way it'll remain radiation dominated until it hits singularity, right? So no cosmic inflation.
Right.
So this way of extrapolating assumes that there is no matter creation. My radiation doesn't interact with anything else. So there is some kind of assumption. This assumption we call technically as a perfect fluid assumption. Okay. We are assuming universe behaves like a perfect fluid. That breaks down every time there is particle production, like at the end of inflation. So you cannot go back continuously. Okay. If you go back, you are assuming a particular state of matter, which is not valid at high energy. The state suddenly changes. There could be a phase transition. Okay. For example, all the massive particles today would become massless at the electroweak phase transition, because Higgs gives them mass much later at lower scale, not at higher scale. So this kind of sudden quantum field theory processes would not be captured by classical GR kind of intuition. Okay. So we should not do that. We should not stretch it back all the way up to Planck scale. Even before Planck scale, things change. For example, baryogenesis happens.
Right.
See the point, right? So that's why Big Bang theory has to do with plasma today, not to take it to beyond Planck scale and all the way to.
I think that also explains why we need to study quantum field theory in order to understand what exactly happens at
Yes.
levels
So,
where gravity breaks down.
yes, you have two sides of Einstein equation. The first side, which I showed as Hubble constant, Hubble parameter, and the second side where you have density, right? This Hubble parameter and density, how they are related, is decided by Einstein's theory. But what kind of density can you have? What is the relation between density and pressure? That is decided by quantum field theory. So it sits right there. You can't ignore it. You can't. I can't just put a negative energy density, for example. Okay, so
Yes. Right. Thank you.
Okay, so we'll try with Aditya again, but before that, we have a question about CMB. So the CMB is a source of so much we know about modern cosmology today. So can you comment about the breadth of information we can derive from it? Starting from being able to predict temperature of the early universe or structure formation, what other information can we derive? And especially in your work, you study the universe when it was very, very young. So does the CMB carry information that's relevant to your study?
fantastic question. Great, I'd love to answer this. Okay, let's go to CMB. Here. This is CMB. Okay, this is the temperature of CMB. Great. First thing, if I look overall, it looks almost smooth up to 4 decimal places. So it verifies that universe was in a smooth plasma state. Second thing it explains is these fluctuations, the presence of these fluctuations. Okay. So it tells you that all the structure formed from these fluctuations. But you have to start from here, from these CMB fluctuations at early times, all the way up to the galaxies and stars and all this cosmic web that I showed you in the beginning, right? So you have to make a transition from here to there. So you have to evolve. Okay, there's some dynamics happening, and how it evolves depends on what kind of matter is there in the universe. So if you play around the matter, suppose you put a little more dark matter, a little less dark energy and kind of stuff. What is going to happen is that you cannot go from here to the today's universe. So there is a unique choice of matter that you have to choose so that you can go from here to today's universe. So it not only tells you how structure is formed, it tells you what is there in the universe. Okay. In particular, that diagram is a visual diagram, which we call in position space. This is in the which we call in momentum space or spherical harmonic space. It's the same information here. So basically, the first, let's say where is the first peak happening? It's happening about 1 degree, if you can see. This tells you what kind of medium was there in the early universe. Okay. it tells you what was the density of the medium, how sound could travel, how fast sound could travel. So you know the medium in the early universe here. Not only that, it also tells you how far is CMB from you in distance. Okay, and how far it is in an expanding universe depends on what kind of matter you put in the universe. So you have some idea about what is there in the universe. Second thing, that you can take ratios of these peaks. For particularly, you can take ratio of this and this. This is going to tell you how much dark matter is there relative to how much normal matter. I hope I could explain it. It will take a long time to explain why this is so, but you can understand by the following, that when I have this plasma and I have these tiny fluctuations, so I have some high density somewhere, and gravity is trying to compress it, but there is a photon pressure in the plasma. It's trying to expand it out, so it's oscillating. If I put a lot of dark matter, the oscillation won't be that effective because it will help in pulling. But if I put a lot of photons and electrons, the oscillation will be fantastically possible, because they will always have a push, a pressure outside. So by balancing this gravity and pressure, you can actually find out how much dark matter and normal matter is there. Okay, and then the overall amplitude and the shape of different peaks and the height of different peaks would also tell you what kind of dark energy is there in the universe. So it actually tells you a lot of information, just this diagram. But this is just temperature diagram. We have many other diagrams. We have temperature versus polarization. Okay, that tells you something else. Then you have polarization versus polarization. A particular polarization, which is called B mode polarization, is related to gravitational waves. So if you measure that and you see some particular pattern, it tells you that there were gravitational waves in the universe. So this is our playground, really. This is like what is Large Hadron Collider to particle physicists, or Stanford Linear Accelerator to them in the 60s, is what CMB to cosmologists today. And it not only tells you what happens at the time when CMB was emitted, it tells you all the way from there all the way until today what happened, plus what happened in the past also. Because if you change the past, what happened at CMB will change. So what happens here will change. So we will see the difference. Okay. So this is the playground. So polarization, yes, you should know. I didn't show the polarization. So that's something extra.
Yeah, Ankita, you had another question?
No, actually I was about to ask Sagarika's question.
Okay,
No question
yeah,
from
sure.
my side.
No questions. All right. So somebody asks, are WIMPs a good candidate for dark matter? On YouTube, yeah.
Again, it'll take a long time. I'll try to make it short. If we take the word WIMP very seriously, it means that the rate at which these particles interact with each other and with the rest of the plasma is very similar to the way neutrinos interact with electrons, for example. And I know how they exactly interact, their rate of interaction. So I know where. So initially they will be interacting fast, and then they will not be able to interact because the universe will take them away in some rough sense. So there will be time when they will freeze out. They will freeze interacting with each other. And depending on where they will freeze, when they will freeze out, depends on how well coupled they are to each other, or how efficiently they were interacting. And if I fix that, I'll say that's a weak interaction, neutrino kind of interaction. Then I know where they will stop interacting. From there until today, I know how they will evolve. So I can calculate how much such dark matter should be there today. If I do that, a miracle happens. If you take typical mass of these particles to be around GeV and MeV, a miracle happens and you get exactly 27% of dark matter today. It's a miracle. So fantastic. But this particular miracle, which happens for this weak interaction, is already ruled out. So they have made it weaker and weaker and weaker, the interaction strength. The more weaker it is, the more difficult it is to detect. So it's going away from this WIMP. So we don't call it WIMP anymore. We call them WIMP-like particles. So they are massive. They interact with standard model particles, but not as well as the neutrinos interact. See, when I talk about photon interaction and neutrino interaction, I would always think photons interact very nicely. I feel the light here, I can see it. But neutrinos are passing through me right now, billions of them, I don't feel them. So in particle physics, we would say neutrino is a badly interacting object. But dark matter is even worse. So compared to neutrinos, dark matter is even less interactive if they are WIMPs. So these are WIMPs, and they are fantastic candidates for dark matter. But we don't call them WIMPs anymore. We call them WIMP-like.
Yeah. Can we have Aditya again on the?
Sir, I had a doubt. Like, if what role did chaos play in the early universe? So, did it play a very big role in the fluctuations that you mentioned earlier, or is it purely quantum mechanical phenomenon that caused the fluctuations?
Sorry, I understood everything. Just the first statement. What plays the role? Could you repeat?
Chaos, chaos,
Chaos.
yeah, chaos.
Okay, great question. Chaos has to do with non-linear equations. Let me explain what is a linear equation, what is a non-linear equation. Suppose I have a quantity which evolves, let's say density of the universe, how it changes with time. And if the equation which governs it is a linear equation, which means that if I give you an initial density, you can tell me what is the final density. If I change the initial density a little bit, the final density will change a little bit. Okay, this is a linear equation. What is a non-linear equation is completely different. It can have two things. First thing, I give you this initial condition, you get this final condition. Then I give you a very different initial condition, you still get the same final condition. I give you completely different initial, still get the same final. This is called an attractor behavior. Okay, whatever initial condition you give doesn't matter. It's like a basin. You have a wash basin and you put water, it always goes to the sink. Right? It's like, so it can have attractor or the opposite, chaos. You change the initial condition a little bit, the final result changes completely different. Okay, you can't even predict. So that's a chaos. So whether there will be chaos in the universe or not depends on what kind of what kind of equation is governing that particular quantity. For example, if you study density, since the fluctuations are smaller in the early universe, it is roughly governed by a linear equation. So there will not be any chaos. But there might be some quantities we can think of, maybe dark matter densities, dark energy density, which could be a chaotic quantity. Then you are at the mercy of, I hate to use the word, you are at the mercy of God. In the sense, if the initial condition was slightly different in the beginning, you will not have this universe today, something else, maybe human beings can't exist or planets cannot exist. Okay. It's possible, but it doesn't seem like.
Okay. Yeah, I think that was a very interesting question, Aditya. There is a YouTube comment. Is there a possibility of creation of primordial wormholes, much like PBH? Of course, assuming wormholes could be existent.
Oh, very much possible. I'll give you one scenario which I know. So everybody knows quantum mechanics, okay? So suppose I make a potential. In quantum mechanics, you have a potential in which the particle moves. Okay. Suppose I make a potential which has two wells. Okay, so there is a well which has a higher height, and then another well which has a lower height. If I put the particle in the higher height well at the minimum, I give it no kinetic energy, just leave it there. Classically, it will just stay there. It doesn't have energy to climb the mountain and then come down. But quantum mechanically, it will tunnel to the lower state. Okay, so it will tunnel. When it tunnels, it's usually a first order phase transition. It's like bubbles. So when you heat water, you see random bubbles of vapor. Okay, and finally those bubbles will grow and collide, and finally you have just water vapor, no more water. Similar things will happen. You have random bubbles of low potential energy universe. Okay, so you'll create them, and you can calculate in Einstein's theory what would happen. What would happen is the low. So I have a space filled with high energy vacuum, some energy, and from there I will tunnel into a low energy at some space. So I have a bubble of low energy. That thing will expand at the speed of light, almost. Right, try to expand at the speed of light. Such a universe can have very unusual connection between different points in space. A wormhole is basically a weird connection between two points in space. You would think let's think of one example. You have a ball, right? and you make a hole here. I remember when I was a kid, there was balloons and they would make it an apple by joining both the ends through the third dimension of the balloon. So something like that. So you have one connection over the surface, but then another connection inside. Okay. So similar things are wormholes. Such things are possible in this particular scenario. I can give you an example. Read the work of Alex Vilenkin on primordial black holes from vacuum tunneling. Okay, and then so it answers both of your questions. You form primordial black holes as well as you form wormholes. So it's possible.
Okay, on those lines, can you comment about vacuum energy itself and kind of the big problem of the actual, value of what the energy is? I guess there are two different predictions, one coming from quantum mechanics and the other general relativistic. So the contradiction.
It's the biggest problem in physics. Yeah. This is something I can talk about hours, but let me talk in 3 minutes. So, in particle physics, what matters is the energy difference between two processes. That's all you measure. You don't care what's the actual energy. When you were in 12th class, your teacher taught you that if you take a potential, gravity, mgh, gravitational potential, but you take anything as zero, right? Sometimes you took the higher place as zero and lower place as negative, or sometimes the lower place as zero and higher place as positive. All it mattered is the difference in potential energy. This is true in particle physics, but not in GR. GR is very sensitive to the actual value of energy density. Okay? So you can from particle physics, you can calculate that just from the fact that there are in the universe there are fields. There is a Fermion field, electrons. There are bosonic fields, photons and Higgs, and all this field. And also there are phase transitions which happen in the universe. From these facts, you say the overall lowest possible energy in the universe is non-zero. It is non-zero and it is necessarily greater than, I'll convert it to SI. It's necessarily greater than 10 to the power 10 to the power 8 GeV to the power 4th, which would be something around 10 to the power 50 gram per centimeter cube, something around that. It should be at least that much vacuum energy, but you won't see it day to day life because you measure the differences, so it doesn't matter. But in Einstein's theory, if you have that much vacuum energy, 10 to the power 50 gram per centimeter cube, it is going to make your universe inflate. Remember inflation, I told you that you have a scalar field which has some kind of a height and a kinetic term. As long as the height is higher and it's moving slowly, it inflates. Another thing which can inflate the universe is a vacuum energy, like this, a constant energy inflated, which is also what we call dark energy. So it's going to inflate our universe. But it's going to start inflating our universe very early, when universe was less than a second old. Also, it will expand it, inflate it at a rate which is much faster. But we don't see that. We see our universe didn't start accelerating until 9 billion years. So it's now accelerating. So there is a mismatch of at least of 60 orders, 50 orders, right? You can push it a little further to Planck scale, it will become around 120 orders of mismatch. So you have observed a vacuum energy or something like that. Its value is 10 to the power minus 29 gram per cc. Your theory predicts it at least 10 to the power 50 gram per cc. So 2950 is around 80 orders of mismatch already. This is the biggest mismatch of physics has ever done. And it's not as loose as this. The quantum theory, which predicts many other quantities up to 10 decimal places. Theory will say it should be 2.1679888, and you measure it and you really get up to 12 orders. The same theory is failing by 60, 70, 80, 120 orders. Like it says it should be 1, and actually it is 10 to the power minus 120. So that's the problem. Do I know any way to solve it? Yes, there are ways to solve it. One way is that you create this vacuum energy. You have some vacuum energy. And this vacuum energy is a combination of many terms. Okay? And these terms there are many terms. They come positive, negative. So if you try to take one kind of combination of these terms, you get something, a very high positive number. You take another kind of combination, you get a very high negative number. Then you take a particular combination, you get a very low enough value, like we see in our universe. This can happen if all these combinations are happening. So you need a multiverse. There are many universes where this vacuum energy is being contributed from all sorts of positive negative terms. They cancel sometimes and you get a low vacuum energy universe. They sometimes don't cancel and you get high vacuum energy universe. Whatever is the story, let me tell you, if the vacuum energy was higher by 2 orders than what it is today, or it was lower in the sense we were negative, we would not exist. That is for sure guaranteed. Okay, so I mean, so there is anthropic arguments that you could not exist in anywhere else but in this universe, because if it was different, you would not exist. That argument can be applied if there are other universes too. If there are no other universe, just one universe, and still all the conditions are set for your survival, you would probably become religious or something. Okay, so it's a serious problem, and we don't know how to solve it completely, but we have ideas how to solve it.
Okay. So we could end with that being the biggest question of physics. I guess we have a couple of more on YouTube. What should be the initial conditions for inflation? Maybe we can have a rapid fire round where you can try explaining it within 2 minutes. What should be the initial conditions for inflation?
It's quite generic. You don't have to. For inflation to start, you need kinetic energy to be lower than potential energy. You could start with high kinetic energy, but because there's a friction term which I showed, it will quickly become potential dominator. So it's quite generic unless there is a large curvature in the beginning. Then what will happen is before inflation starts, universe will collapse, big crunch. That problem I don't have. I have some ideas how to solve, but nobody has solved. So yes.
Apart from the mysteries of dark matter and dark energy, are there any other questions that a cosmologist aspires to solve?
Name it. What is space? What is time? How many dimensions of space are there? What is quantum theory of gravity? What is dark matter? Oh, you have said that. Okay. Matter antimatter asymmetry. Why is it there? Why does our universe has 3 dimensions, not 4 dimensions, 6 dimensions, 3 space dimensions? Why the cosmological constant, if it is 0 or small, why is it small? Why is it not big? Why are the laws of physics the way they are? Do they change over time or not? Yeah, so anything, basically.
Yeah, pretty much most things. Okay. Does gravity have a definite range?
Range, I think it means how far it can go. As far as we know, it goes all the way. It's almost infinite. It doesn't have a finite range. It could have a very small cutoff somewhere if it has a velocity, but it doesn't seem like.
Okay. Yeah, with with the development of interferometers and specifically sensitivity to gravitational waves, what can a cosmologist expect in terms of answers in the future, in the next decade, perhaps, coming from gravitational waves?
Not in next decades, gravitational waves may solve the problem of Hubble tensor because there are independent way of measuring it. But maybe give me 3 decades, they can tell you whether inflation happened or not. So origin of structure in the universe. And you, in general, keep in mind that gravity, it's very difficult to stop gravitational waves. So they would come all the way from the beginning of time. So you want to see the beginning, you really want gravitational waves. Okay. Photons don't come. It was opaque. Universe was opaque earlier. So yeah.
Okay. You spoke about quantum fluctuations, but what caused the quantum fluctuations?
What causes is quantum laws of nature. That if you have heard Heisenberg uncertainty principle. So any field, if you have it, there is quantum fluctuations here in this room. I don't feel it because in Minkowski space on large scales they decay. But if you have, by Minkowski space I mean normal space, not expanding. But if you have expanding space which is accelerating, there they don't decay away. They become constant after a while. So they initially decay and then they become constant. And that thing creates galaxies. It's a complicated thing. I'll explain maybe sometime later. This is a
sure. Okay, yeah, I guess last question to wrap up. Do you have any comments about alternate theories of gravity? This is coming from me, but if you have any comments
So
on like maybe Milgram dynamics or...
definitely gravity is going to change as you go to very high energy. If you go to Planck's, very close to Planck scale, it's going to change. Whether gravity would change at low energy on large scales, these are interesting ideas, but no observations point that they are necessary. Like there is no observationally there is no motivation to change Einstein's theory at low energy. But it is almost guaranteed that it will not be valid at very high energy. At Planck scale, very early universe, it has to be changed. So yes, we will have to face that reality someday when we.
Okay, with that, we'll end today's event. So thank you so much, Swagat. I think that was very, very informative, and we learned so much. We covered so many different topics. So the Q&A was, I think, very, very good. Thank you all viewers for tuning in, asking really good questions today. I think we had some brilliant questions coming in from even the YouTube viewers as well. Thanks once again, everybody, for your time. Just a closing remark: if you would like to be part of, future events by Naxxatra, whether it is the free lecture series, we also offer free research projects coming up in the month of October. But before that, if you would like to be part of the intensive, training program that we have called Equinox, then yeah, you can just check the description, and you can use the application form to apply. We have a deadline on the 5th of September, so please apply before that. You'll find, we have over 10 to 12 speakers like this, and many, many different topics. So yeah, hope to see you all over there. Once again, thank you, Swagat.
Thank you very much.